Okay, hello everyone. I'm Joseph, and today I'm glad to represent the TeamZ Lab for this sharing. And first of all, I would like to thank the organizers and Kaggle for hosting such a meaningful and valuable competition. I also appreciate you for attending this meeting. And here is the introduction of our team. Our team members are all from China, and we all have plenty of experience of data science computation in Kaggle. And each of us have won several medals. This is also our vocation. Okay, and the first part I would like to introduce is about the data processing. In this computation, we know that training data is super important for the computation. And according to the GitLab, we know the Kaggle data is sampled from the full low-resolution dataset. So we try to download the raw data from the GitLab, and we use the year 1 to 7 and the first half of the year 8, totally around 75 million data samples. And for the validation, we sampled the July to December of the year 8 and the January of year 9 as our validation data set. The sample stride is 7. It's about 0.8 million. But the mean and the standard deviation value for normalization are calculated only on the computation data. Besides, we found that some labels have correlation with the features. In the patent Q0002, from the number 12 to 28 have a linear relationship with the state Q222. And for the equipment, we use 3 RTX 4090 with 308 gigabyte memory. The next part is about the training method. First, we train our model on the all 386 labels. And then we divide the 386 labels into 7 groups, each of which are a series of measurements of the atmospheric targets. And the last group consists of the 8 scalar targets. After training all the labels together, we fine-tune for each group again. The model's output size is still 368, but we load the model weight and change the loss to only focus on one group at one time. So since we have 7 groups of the series target, so we need to fine-tune the model 7 times. And this is the most effective trick in our solutions, which give us the edge over other teams. And through this trick, the score would be improved at least 0.001. And here is an illustration of the group fine-tuning. After we train the models together, we change the loss. From the code. We can see that there is a GID. For each group, we use the number of the group as the GID to only make the loss focus on the specific group. And for learning rates, we first try to use the cosine with warm up, but finally we change to use the cosine scheduler with restart and early stopping. To balance the performance of the cost of time and the performance, we finally choose 9 epochs with 2 periods. The first period is 3, and then the learning rate will restart, and then go with the next 6 epochs period. And the best score will always occur in the last 2 epochs. In theory, this one can help the model to escape the local minima and coverage more effectively. So, and for the separate group fine-tuning, each group will be fine-tuned only one epoch. And then next is about our optimizations. We choose the smooth L1 loss, and we also design an auxiliary diff loss. Through our experiments, we found that the smooth L1 loss is the best loss for us. And since this is a multi-level regression task, the smoothness can improve the optimization process and leading to a more stable convergence. And for the auxiliary loss, it really helped our models to learn better. For each series group levels, we calculate the difference of the real values of the adjacent targets and the difference of predicted adjacent targets, because we know that the neighboring level may have some relationships and won't vary too much. So it's just like to describe the changes between 2 adjacent levels and then add a constraint. Okay, the next one is about the models. First, we use the hill climbing method to do the example. One intriguing aspect of the hill climbing is that it includes the negative weights. And from the chart we can see that the last 4 models have the negative weight. So although the performance of these ones not good enough, but they contribute with another way as they have a negative weight. And next, I want to introduce some single model structures. All our models are based on LSTM. This is due to our findings that LSTM significantly outperform other structures, such as the convolutional neural network or transformers in this computation. And inspired by the ResNet and the transform, all our models incorporate the residual connection. In our experiments, adding the residual connection makes the model's coverage faster and perform better. So from the figure, we can see that we designed a REST LSTM block. And we just stack many these blocks and with a linear layer. For the diversity, we also use the convolutional neural network as the encoder. So we design a different size of convolutional neural network and then stack with many LSTM blocks. The next one is LSTM with the member block. And the models will mix the LSTM and the member achieve very good scores, both offline and on the leaderboard. But despite the individual member-based models not outperforming the pure LSTM structures, it also brings the diversity to our final example. And this is another kind of LSTM combined with the member. But this time we introduce the member into each blocks of the LSTM. But it also not outperform the pure LSTM. Just bring some diversity for our examples. Okay, and next is our team's highest performing single model, which provides best results in local scores and private scores. The difference of this one is we use the different ways to the inference part and the residual part. And from the figure, we can see that the residual part, we give it a 0.3 weight. And another difference is that we changed our custom loss function in this model. Is for the smooth L1 loss. It has a parameter called beta. The default value is 1, and in this model, we change the parameter to 0.5. Here are some other models, not very good, but provide some diversity for the example. One is we stack the convolutional neural network with multiple layers of LSTM and one layers of transformer with a final linear layer. Another one is multi-layers rest convolutional LSTM blocks with time-distributed Foley connection layers. We can't say it works too much, but it brings the improvement in our example. And here is the code for the time distributed. Basically, all our models don't differ too much. Just some different layer types or nuances in parameters. Okay, guys, that's all. Thank you.